In this video, we're going to look at mathematical sentences and equality. So let's start with a few definitions. An algebraic expression is a mathematical phrase that contains numbers and/or variables that may involve operations connecting them, such as addition, multiplication, etc. A mathematical sentence is a statement that shows a relationship between two or more numeric expressions or algebraic expressions. We say that two algebraic expressions are equal if they have the same value, and we will call a mathematical sentence that describes the relationship of equality an equality statement. So we use an equal sign to denote equality. Okay? So here's some basic definitions, and again, we're going to look through examples, and this may not have a lot of meaning for you now. We look at them, we review them, and then make sure you refer back to these definitions later once you have a better feel for what they're representing through examples. Now, when we are dealing with a numeric equality statement without variables, so what we've done before algebra, the equality statement is either true or false. Okay, so on the left here we have true statements. 3 equals 3. That's true. Here we say 5 minus 3 equals 2. That's also true. This one may look a little bit different to you. We'll talk about this in more depth later. But notice the left-hand side of the equal sign, 2 plus 5, well, that's 7. And the right-hand side, 1 plus 6, is also 7. So these are true. Okay. Or we can have a false statement. 3 does not equal 5, so it says 3 equals 5, so that is false. A corresponding true statement would be 3 does not equal 5. Okay. 5 minus 3, it doesn't equal 6, so this is false, and similarly this is false. Now what happens when we start using algebra and variables is that we will find that some equality statements can be conditionally true or sometimes true. Okay? So we have numbers, it's true or false, that's all she wrote. Now we have variables. We don't know what the letter represents, if it represents a specific number or a changing value. Okay? So it can be true for some values of the variable and not for others. So for example, x plus 1 equals 3. If I replace x with the value 2, and I add 2 plus 1 the left-hand side, it does in fact equal 3. So this statement is true when x equals 2. What if I put in a different value for x? Maybe 0, 3, or 7. I'm going to put in 0. If I replace x with 0, and I add 0 plus 1, I get 1. That is not equal to 3. So 0 is a value that makes this statement false. Okay? And then you can look at these other examples. So that's the idea we want to look at here now, is this understanding that some values of a variable can make it true, make an equation true, and in those cases we will say that it is conditionally true or sometimes true. So let's look at some examples. Truth, value, and equality statements. So these are equality statements, and we're going to determine their truth value, whether they are sometimes true, always true, or never true. And we're going to use the balance scale to visualize the equation and justify our reasoning. So looking at this scale, the idea we're going to use here is this is the number 2. C is a variable that represents some specific number, or it could be a changing value. So we're going to pretend that these numbers are weights. And if this equation is true, when we put them on the balance scale, the left-hand side of the equal sign should balance with the right-hand side. So let's use, for the left-hand side, I'm going to say that this triangle is a weight, and its weight is C, whatever C may be. And I'll use a square for the number 2. So on the left-hand side, we have C and 2. And on the right-hand side, we have 2 and C. So convince yourself, if C was say 5, that if we put these two on the same side together. That's the same as addition. And now the question is this scale balanced? And I hope you agree that it is. Okay, it doesn't matter where we put the C or the 2. We have the same weight on both sides of the scale. So this equation is always true. Let's look at the next one. Here we have a plus 2 equals a plus 1. Okay, so I'm going to let's put a in a square this time. And I'm going to use little triangles to represent 1. So I know we have 2 here, but 2 would be 2 1s. Okay. Now let's approach balancing this scale in a different way this time. So the last time we took everything on the left, put it there, put it on the left-hand side of the scale. Then we took everything on the right, put it on the right-hand side of the scale. Let's look at these instead and try to keep them balanced along the way and see what happens. So we know both sides have an A, so I'm going to put an A on both sides. And notice that the scale is balanced. They both have a weight of A on both sides, whatever A may represent. 10, 20, 13, 4, whatever. Okay. Now, the right-hand side has 1, the left-hand side has 2. So we know 2 is 2 1s, so I'm going to add a 1 to both sides. And you can see right now that the scale is balanced. They both have A plus 1 on both sides. Okay. Well, we have the right-hand side, but the left-hand side has an additional 1. So notice, if we add an additional 1, maybe you can visualize this, the scale would tip downwards because the left side would be heavier. There would be 1 more. Okay. It doesn't matter what A is, these two will never ever be equal. Okay. So this is never, never, never true. Sorry, that's my Taylor Swift imitation. Okay. Let's look at the last one. So now we have a whole bunch of letters, okay? But don't let them bother you, okay? Remember, these are just representing numbers that are either fixed or that we don't know, okay? So let's make, how about H will be a triangle. We have M's, we'll make that a square. We have an N. I'm going to make that a circle and we'll pretend it won't roll right off the scale. And then we also have a P. How about, we can all draw a heart. Let's use a heart for a P. Okay. So now let's use keeping the scale balanced. Okay. So first we have an H on both sides. So if I put an H on both sides of the equation or on the scale, it is currently balanced. Okay, the left-hand side has an M, but the right-hand side doesn't. It has a P, so I'm going to skip that for a minute. They both have an N, both sides of the equation. So I'm going to put an N on both sides of the scale, and it's currently balanced. So now our question is, the left-hand side has an M, the right-hand side has a P. Let's kind of hover these up here. So now we know that M and P are not the same variable. And the reason is we gave them different letter names. Okay. So what we want to know, they're not the same variable, but could they ever be equal? Okay, so two things can be different but still sometimes equal. So let's make up an example. So say M is Michael's age. Let's use Mike for short. Mike's age. And P is Phil's age. Okay. Well, it's possible that Mike is older than Phil. So maybe Mike is 10 and and Phil is 8. Okay. So if this were the case, the scale would tip this way because M would be heavier than P. It's possible that Phil is, let's say, 12 and Mike is 1. So if this was the case, then when we put the P down here, this side would go down, this side would be heavier. But it is completely possible, since we don't know Mike's and Phil's age, that Mike and Phil could be the same age. So suppose Mike is, 12, and Phil is also 12. Okay? So they could be the same even though they're representing different variables. So we're going to say that this equation is sometimes true. It's possible that this side is greater than the right side. It's also possible, like we saw, that the right-hand side is greater or heavier than the left-hand side. And it's possible that they are, in fact, equal. Okay? It's sometimes true, and specifically when M equals P. Okay? And we use the example of Mike and Phil having the same age of 12. It could be 1 or 75. Okay? So this is conditionally true, sometimes true.